So in this lesson, we're just going to work with simplifying radicals with variables. So it might seem a little bit different from what we did with the radical equations, but we need to work on simplifying just radicals independently. Okay, so some properties that we have to understand is if we have a radical like this with things being multiplied on the inside, we can split that apart to a radical with both of the things inside with that same index, okay? That little thing there is called the index. This is the radical sign, and these are the radicands, okay? So we have these properties we're going to be using. Okay, so we can break apart radicals with multiplication. We can also break apart radicals with division or quotients, okay? So this one is a similar property. We're just breaking it apart where we have a radical on the top and the bottom. And we've worked through these before, okay? This is just a little implied thing. I can't have a 0 on the bottom of my fraction, otherwise it doesn't work, okay? So the next new thing here is rational exponents. Okay, so we're going to have fractions in the exponents, and we've talked about these in previous lessons. Now it's just something we got to do with different than like a half or a third exponent, all right? So this is how we generalize it. We have a to some power m over n, or mnth power. The n is going to be the index, so the bottom number is my radical number, and then the top one is the power, okay? So it goes power over index, or power over root, okay? The n is here, the m is there, all right? And likewise, we can do it this way, where we have the nth root of a to the m. So the m can either be on the outside like this, or the inside like that. Whichever one makes it a little bit easier, okay? And then we have negative exponents as well. So remember what negative exponents are going to do. They're going to take my number and they're going to flip it, and it just does the same thing on the bottom of that fraction. Okay, so it's just going to turn into a fraction and do the same thing. So let's practice this a little bit. Okay, so we have 16 to the 3/2. I got to remember how it works. It's going to be power over index, or power over root. So this is the root. All right, so this is going to be square root of 16. You can put the 2 in there if you want to, but generally it's implied when it's a square root. And it's going to be raised to the third power. All right. Now, if I thought about doing it the other way, let's say I put the 3 on the inside, like this. That doesn't make a whole lot of sense to do that, because otherwise I'm doing 16 to the third power, which is going to be a pretty big number. And we want to be able to do these as much as we can without a calculator. Okay, so if we're evaluating these, we're going to use PEMDAS. We're going to do parentheses, then powers. Okay, so square root of 16 is a 4. 4 to the third. Okay, that's 4 times 4 times 4. That's going to be a 64. All right, and if you can't do this in your head, you should be able to multiply with long multiplication. All right, that's 16. So 16 times 4, we got to set it up like this. All right, 4 times 6, that's going to be a 24. Put that 2 up there. 4 times 1 is 4 plus 2 is 6. Okay, and that's where you get your 64. So you want to be able to do this stuff without a calculator. There is a no calculator section that you will be tested on with this stuff. All right. Next one, 32 to the negative 3/5. Okay, we'll try this one. So that negative exponent means it's going to make a fraction, 32 to the 3/5. Okay, like that. And then we're going to use our rational exponent properties, where we got 1 over, so this is the root, 5th root of 32 to the third. Okay, so we have a 5th root. That's not like a square root or a cube root. It's a little bit different. So what number times itself 5 times gets me a 32? Well, the way you figure this out is you just kind of start multiplying things in your head, and I would start with the smallest even number. So if I do 2 times 2 times 2 times 2, does that get me a 32? Well, this is 4, this is 8, this is 16, this is 32. So 5th root of 32 is a 2. So this would be 1 over 2 to the third. And 2 to the third is 8. So this is 1/8. Okay, So you have to have the concept of radicals in your head when you're doing these. You can't just do a simple perfect square, perfect cube kind of thing anymore. Okay? Try to do the next two. I would try to do them and then come back and check your answers. So pause the video if you need to. Otherwise, we'll keep rolling on the video. So 64, power over index. So this is the third root of 64 squared. What times itself 3 times gets me that 64? Well, it's not going to be a 2, not big enough. It's probably a 4. So this would be 4 squared, which would turn out to be a 16. So 64 to the 2/3 is 16. Now the last one here, we have a property that we have to use. Not just radical property, this is exponent properties, okay? We have a like base of 4. You could compare this to something like this. What am I going to do with my exponents when I'm multiplying the same base? We have to add the exponent. So this would turn out to be 4 to the 1/4 plus 1/4. Okay? 1/4 plus 1/4 is 2/4, which is a half. So this is 4 to the 1/2. And now we're going to use our fractional exponent properties and change this back into a radical. So 1/2, that's the index, so it's a square root of 4, which is just a 2. Okay, so we kind of got to keep those exponent properties in mind when we're doing this, because now we're doing exponents that are fractions. Okay, so a little bit of radical review with operations and such. Since we're doing nth roots, that means we can have cube roots, fourth roots, fifth roots, whatever, all right? In order for you to follow the rules that you know with radicals, these have to match. It has to be the same index, okay? So since this is a third root with both of these, we could just multiply 12 times 18, okay? That might take you a little bit more brain power if I don't have a calculator. So think of the process that we're going to use here. If you were doing this, then I would multiply 12 by 18, and then whatever number that is over here, it's going to be in a cube root, and I'd end up factor treeing it in a bunch of little factors, all right? What you could do alternatively is make your factor trees over here, okay? Because you're going to be doing the same thing anyways. So let's make our factor trees here, and then we can look for our factors of 3, okay? And let's get rid of this. So since it's a cube root, that means you need 3 of a number, okay? Whenever you have 3 of a number, like this, so I got 3 2s, that would give me a regular 2 from a cube root, all right? And I have 3 3s. So that would give me a regular 3 out of the cube root, which I would end up multiplying those to get a 6. All right, for the next topic, we're going to look at our rules to see if we can put these together, all right? So we know that if we have a square root or a fourth root here, that doesn't work out nice, so you could have to rationalize that. But before we try to rationalize this, we're going to try to put it together like this, so 80 over 5, okay? So that would be using our quotient rule. We can put those 2 square roots or fourth roots together. And then inside there, 80 over 5 is the fourth root of 16, okay? And then you're going to ask yourself, what times itself 4 times gets me a 16? That is a 2, okay? So I'll show you rationalizing here in a bit, but before we do any rationalizing, we want to try this rule, see if we can simplify. If we can't simplify, then we go back to this and we rationalize, right? So trying to get these in simplest form. Okay, we have a cube root of 135. So what we're going to have to do, take that 135 and we're going to break it down. Okay, so 5 and 27 go together, and then we're going to break that 27 down to 3 and 9, break the 9 down to 3 and 3. So since this is a cube root, we got to have groups of 3 numbers. So 3 here, 3 here, 3 here. Once I have 3 of something, that number goes out in front, and the numbers that are left go back underneath there. Okay? And we have to make sure that we put the correct index back where it's supposed to be. A lot of the time, people will simplify these, and they're used to doing square roots, and so they'll forget to put the index back in there. And that changes the answer if I have a square root.
All right, for B, so just like I said before, you should try this first, but it should be fairly obvious that that's not going to do a whole lot for you. 7 does not divide nicely with 8. Okay, and we're doing a fifth root here, so we have to rationalize. So what does rationalize mean? Rationalize means we have to take the bottom and the top times some square root, in this case, some fifth root, in order for that to work out nicely. All right? So you have to find the nice fifth root. So there's two ways to do it. You could ask yourself, what is the perfect fifth root that I can multiply this 8 by to get it to? Or you can do it the way where you break it down like what we did up here, okay? That's the way I like to do it. So I'm going to break this 8 down to a 2 and a 4, and then a 2 and a 2. So I have 3 of a number here. I need 5, okay? So how many more 2's do I need? Well, I need to have 2 more 2's, and we'd have to multiply by 2 more 2's because we are doing a factor tree. So factoring means multiplying, all right? So what we need to multiply by is a 4. That would be this 2 and this 2. Okay? So that process is how you're going to try to figure out what you need to multiply this number by to get it to a nice fifth root. And since I did it on the bottom, I'm going to have to do it again on the top, multiply by that 4. Okay? It has to be in a fifth root, because if it's not in a fifth root, you can't multiply by the other fifth roots. All right? So then we're going to just multiply straight across. So we have 28 on the top, fifth root 28, and on the bottom we have fifth root of 32. Okay, and I don't really need to do this step because I know if I were to do a factor tree with that 32 again, I would have 5 2's. So this is just a 2. So fifth root of 28 over 2. And that's what you'd have to do to rationalize. Okay, now again, you don't want to try to rationalize right away. The first thing you want to do is try to do something like this. Okay, unless it's blatantly obvious, like the 7/8 is fairly obvious, but a lot of the times you're going to have larger numbers like this, so you try to go from here to here, and if that doesn't work, then rationalize. Okay? So next thing, we talked about this in previous lessons, but we're doing higher order indexes or higher indexes here. You want to try to add and subtract radicals. If the indexes match and the number in the radicals match, then you can add the coefficients. So this is an implied 1 for this coefficient. So we would do 1 plus 7, which would be 8, and then I have the fourth root of 10 back with that. All right? So we get to a different concept here, where we have 8 to the 1/5 plus 10 times 8 to the 1/5, okay? So you've got a couple different ways you can do this. We can change this back into a radical. It might be a little more obvious if I do that. So this would be power over index. So it's a fifth root of 8 raised to the first power, and you have a 2 in front of that. Over here, we got another fifth root of 8. And we got something like that. So it would be 2 fifth root 8 plus 10 fifth root 8, which would be 12 fifth root of 8. Okay? If you didn't want to do this step, then you could have said to yourself here that those are both matching radicals. 8 to the 1/5 and 8 to the 1/5, those are both fifth roots of 8, which we could have this answer as well. Okay, so you could have 12 times 8 to the 1/5. All right, but I say this answer is a little bit cleaner. All right? So I would like you to try this one on your own. So if you'd like to pause the video, give it a shot, check your answers. Then you can see if you did it right or wrong. Okay, if you don't want to pause the video, we'll work through it right now. So 54 and 2 do not match. I cannot subtract them. I can't subtract stuff underneath. Okay, I have to have like radicals. So we're going to factor tree this, see what we get. So 2 and 27. 27 is 3 times, not a 2, it's 3 times 9. And 9 is 3 times 3. So we have 3 of a number, and the 2 stays back underneath there. So simplifying, we should have 3 cube root of 2. That's this one after we simplify it down. And then we have the cube root of 2 here. Okay, so those both match, so we can do them. So you want to try to simplify and then see if you can add or subtract. So now we have the same radical here and here. Subtract the coefficients. We should have 2 cube root 2. Good? All right, now I'm going to be throwing some variables at you in these radicals. Okay, so you can ask yourself these questions if you ever get stuck. Maybe circle these or highlight this on your notes so you can come back to this. What times itself gets you that number? Okay, this would be the first thought process I go to get like a perfect square or a perfect cube or fourth or something like that. Okay, so we'd be looking at the 64. When I'm looking at variables, okay, I ask myself, how many groups of that can I take? All right, so I'll be looking at this one. How many groups of 3 in this scenario can I take? Okay, so starting out 64. Is 64 a perfect cube? It is a perfect cube. If you didn't memorize that, you'd have to break the 64 using a factor tree. Break it down using a factor tree. All right, so 64 is 4 to the third. So since that's 4 to the third, I can take that out. Okay, so we have a 4. And then with the variable, I'm asking myself, how many groups of 3 do I have from y to the 6? That's 2 groups of 3, so that y to the 6 would turn into a y squared, like that. Okay? And if you can't think about it that way, another way to do it would be to expand that y. Okay? So I have 6 y's. Y to the 6 is y times itself 6 times. And then I'm looking for groups of 3. So I have a group of 3 here. That gives me 1 y. A group of 3 here. That gets me a second y. You multiply those to get to y squared. Okay? Let's try another one. So I have the 1/3 power. What is the 1/3 power? Well, it's power over index. So that means it's a cube root. I have cube root of 27 p to the third q to the 12th. Okay? So is there a number that multiplies by itself 3 times to get 27? Yeah, that would be 3 times 3 times 3. So 27 is a perfect cube. We get a 3 from that one. And then how many groups of 3 can I get from p cubed? That would be 1 group. How many groups of 3 can I get from q to the 12th? That's 4 groups. So we have 3pq to the 4th. If you don't like the method that I'm discussing here, you can always think about it this way, where I would distribute the exponent. All right? If I distribute the exponent to these, they're just going to multiply. So 3 times the third is the first power. 12 times the third is the fourth power, like what we have there. Okay? So there's a few different ways to do this. I think the grouping strategy is a little bit easier in your head. So like, how many groups of 3 can I get from this? 1 group of 3. How many groups of 3 can I get from that? 4 groups of 3. Okay? So you're using the grouping strategy to simplify radicals. I think that's a little bit nicer on your brain. Okay? Looking at C. Can we simplify inside here first? No. M and N are 2 different variables. So we use our quotient rules. We separate this. And then we simplify it. Okay? So how many groups of 4 can I get from M's? 1 group. That's just M to the first. And I can get 2 groups of N. So I have N or M over N squared. All right, and 1 down here is a little bit more difficult because we have fractional exponents kind of all over the place. So you have to think about how exponent properties work here. So let's look at these first. 14 and 2, those are just going to simplify to a 7 on the top and a 1 on the bottom. So we took care of those, just taking out a 2. And now with the x's, all right, we do it the same way. We're moving the variables to where the larger power is. The power up top is a 1, so we're going to take 1 and minus 3/4 from it. Okay, so it'd be like this, x to the first minus 3/4, and that'll be on the numerator up top. So that's just going to be x to the 1/4 after we simplify. And then the y's, that's going to stay where it's at. We don't need to move it because there are no other y's. And then the z, that has a negative exponent, so that needs to move up to make that a positive exponent. And we have something like that. So I don't even need the 1 on the bottom. After I simplify, this is what we get. Okay, so we're just using exponent properties for that one. We just have fractional exponents. So shouldn't be too crazy. If we have something that doesn't work out nice, then we're still using that grouping method, but it's kind of like a factor tree idea. Okay, so this one, I have a 5th root, and I'm trying to simplify this. 4 is not a perfect 5th root, so you can't really do anything with it. And if you tried to factor tree the 4, you'd only have 2 of a number. All right, but that's the right method we want to use. We want to try to factor tree these numbers. They're generally going to be a little bit larger if we have a 5th power. Okay, so the way we handle this is we kind of go through one thing at a time. If we can't do anything with it, we write it back underneath. If we can do something with it, we pull out what we can, and then we write the stuff back underneath that stays underneath there. Okay, so how many groups of 5 can we get from A to the 8th? Well, we can get 1 group. And then you ask yourself, how many are left after I take out that 1 group? There's 3 left. I can't take any more out, okay? If that's hard to grasp mentally, think about it this way. I have 8 A's, okay? I'm taking a 5th root, so I'm taking 5 of those to simplify, okay? If you take 5, then that gives you 1 of them outside of the radical. And those are used up, and then you write the other ones that you haven't used back underneath there. So there's 3 left after I take out that 1 group, giving us A to the 3rd. All right? Same idea here. How many groups of 5 can I get from that? Well, 15 would be 3 groups, but we don't have 15. So I can only take 2 groups, which would be taking 10 of them away. Okay, so 2 groups gives me a B squared. I'm taking 10 of those away to get my 2 groups. I have B to the 4th left. Okay? And now this one, how many groups of C's can I get? Just 1 group. So C to the 1st, and there are no C's underneath there because I used them all just for that 1 group. Okay? So that's the thought process you want to have when you're simplifying radicals that don't work out to be perfect squares, cubes, 4th, 5th. Okay? We have to kind of use that idea with something like this. Okay? You can simplify right away if you want to. We can kind of use our quotient property where we're doing this. We're splitting it up. Okay? And then you have 2 options that you can do from here. I can jump to rationalizing right away, or I can simplify and then rationalize. And how do I know I'm going to have to rationalize? Well, 3 does not perfectly go into 8. So that's how you know you're going to have to rationalize, because we have a radical in the denominator. So if I want to simplify first, okay, I'm just leaving that cube root of x up there. I'm pulling out groups of 3, so I can get 2 groups of 3, and then I have to rewrite what's left. So 2 groups of 3 would be like taking 6 of those out. I got a y squared left. Okay, so then you need to make this work. We need to give it the amount of things it needs to work out nice. Since this is a cube root, I need 3 of something. So what you're going to do is multiply this by the cube root of y. Since I do it on the bottom, I have to do it on the top. Okay? And then when I multiply by the cube root of y, once I figure that out, I just finish out multiplying and simplifying. So down here, I'll have y squared times the cube root of y to the 3rd. That's going to simplify to another y. And then I'll have y to the 3rd on the bottom. Okay? That's one way to do it, where you simplify and then you rationalize. All right? That takes a little bit more steps to get where you want to get to in the end. The other way to do it is just to think about what I can turn this into, or how can I get that to be the next group up. Okay? I'm looking for groups of 3. I only have 8. But I know if I have 9 of these, that would be 3 perfect groups. Okay? So I'm going to just start right away by multiplying by a y on the top and the bottom, and then simplify that. Okay? And then I just simplify one more time, and I'm done. So cube root of xy, and we said we were making 3 perfect groups with this, so this would just be y to the 3rd. Okay? Oops. So this method, I like this method a little bit better because it's a little more efficient. I'm just looking to make this a larger number, and I'm only simplifying one time in the end. If we did it the last way, where we have to simplify, you're going to have to simplify in the end again anyways. So you'd have to simplify twice with the first method. Okay? This way is more efficient. Let's move this down a little bit so we can put both of these in the same area. Okay, so C. All right, on C, we are going to have to try to simplify first, and there's probably going to be some rationalizing going on. All right, so your brain might be in rationalizing mode, which if you split it right away and rationalize it, you can get to the same idea, right? But what I probably should have done first is looking at the 12 and the 3, I can simplify those. That's going to make it quite a bit simpler because I don't have to worry about rationalizing that 3. So let's just take a 3 out of here. And I got 4xy squared, and I know we're going to be splitting that to rationalize next. And I'm here. So how many more z's do I need to make it a perfect group of 4? The answer is 2. So I need to multiply this by 4th root of z squared to make that a perfect group of 4. Okay? And then I just go from left to right after I figure that out. So 4xy squared z squared, that's all in a 4th root. And the bottom, I would have, let's just write it out, 4z to the 4th, which I could have saved a little bit of time, and I knew that this would just be a z. Okay? So final answer is this. Okay? So I had to use a couple different methods there to get that one. And then this one's an old one, but a good one. We haven't done a whole lot of those with square roots yet, so it's good to look at that. You did this in Algebra 1, possibly a little bit in geometry. You have something plus or something minus a square root in the denominator. Okay? We're going to have to rationalize with conjugates. So if you remember when we had our discussions of complex numbers, we had to rationalize using conjugates. Same idea. You're going to have to rationalize using conjugates. However, these have square roots. So we're going to be getting our practice with FOILing out square roots and distributing out square roots. All right? So that goes into there. 5 root 5 minus, and then remember, since this is in a radical and this is in a radical, both square roots, we can multiply them. Root 10 over, multiply out the bottom. So 5 times 5 is 25. That's this one. Now we take 5 times negative root 2. So minus 5 root 2. And then root 2 times 5. So plus 5 root 2. And then minus root 2 times root 2, which is just 2. Okay? After you FOIL it out, you should recognize that I have some things canceling out in the bottom, which is good. So I'll just have 25 minus 2, which is 23. And then my numerator, 5 root 5 minus root 10. And if you can't simplify anymore, you call it a day. Okay? An example where you could simplify, let's say I had something like this. 4 root 3 over 4. Okay, let's say I ended up with something like this, hypothetically with a different question. You'd have to look at all your coefficients and integers or whole numbers to see what you can simplify. Since these are all even, I would take a 2 out of everything, and this would be like this. Okay? I can't take that 2 out of there because I'm not doing it out of there. So that would be breaking operations if I only did it to one thing. Okay? So that's what this would look like if I simplified it. All right? So that's pretty much all of the concepts involved. Okay? The rest of it is just practice. So if you would like to watch the practice, I'm going to make a separate video with extra questions in it covering these. But your homework is the worksheet, okay? And 51 to 55 odds, okay? So if you are done, if you understand the concepts, get started on the worksheet. Otherwise, the separate video will include extra practice questions.